Hey everyone, and welcome to Circular Motion. Think about any time you've been on a carnival ride, or even just driving around a curve. What is it that keeps that object, or car, from simply flying off in a straight line? Our central question today is, what is the force doing the bending the path? This isn't just about speed, it's about the constant change in direction. By the end of this lesson, you'll be able to predict the forces needed for everything from satellites orbiting Earth to roller coasters plummeting through vertical loops. Get ready to master the physics of curves. Remember Newton's first law? Objects want to keep doing what they are doing. If there's no force, they keep moving straight. We use geometry, specifically similar triangles, to visualize how the velocity changes. If we look at the velocity vector over a small time, we see a right triangle forming. The hypotenuse represents the initial velocity, and the adjacent side relates to the final velocity. The change itself is what we calculate. The rate of change of velocity, or acceleration, is what defines this geometric relationship. This process solidifies the formula. Since $_c equals v⁻²/r$, we simply substitute this into Newton's second law, $F_c equals m\v⁻²r$. This inward force must come from something: tension in a string, gravity pulling you down, or friction resisting motion. The car is moving horizontally. The only horizontal force component pulling it inward is the static friction between the tires and the pavement. Plugging in our numbers, we calculate the necessary centripetal acceleration, $_c equals 20^2/$50. At the top, both gravity and the normal force point downward, directly toward the center. They combine to provide $F_c. Therefore, $F_c equals N plus mg$. We set this equal to $mv²/r$. The calculation is $N plus mg equals mv²/r$. We solve for the unknown normal force, N. This example shows that even when calculating $N$, we are always solving for the necessary net force required for the curve. For an inclined plane, we use trigonometry. The horizontal component of the normal force, $n/sin⁡, acts inward, providing $F_c. We equate this component to the required centripetal force, $n/sin⁡ equals mv²/r$. This allows us to find the necessary angle $h for a given speed and radius, showing how the track is designed. At the minimum speed, $n equals $0. We set $F_c equals mg$. Thus, $mv²/r equals mg$. The mass cancels out, leaving $v⁻² equals gr$, or $v equals \r$. This speed is the absolute minimum to complete the circle. This concept is vital for safety engineering, ensuring roller coasters don't fail. Do not use centrifugal force in your calculations. It violates the laws of physics as we usually model them. We are analyzing the motion from the ground frame, where the net force is always $F_c pointing inward, toward the center. The true force is always provided by a physical interaction, like friction or tension, never a concept called centrifugal. Picture a spinning ball on a string. Does the ball itself point toward the center? No. Its speed vector is tangent, like the edge of the wheel. What is pointing toward the center is the acceleration. This acceleration is what constantly changes the direction of the velocity vector. If you draw the velocity vector at any point, it's perpendicular to the radius. The acceleration vector is parallel to the radius. When we talk about orbital mechanics, we are seeing circular motion in its purest form. The Earth's gravity is doing all the work. The gravitational force acts as the centripetal force. $F_c equals F_g equals g\frac m/r². The relationship is incredibly stable, which is why satellites can maintain orbit for years. They are always falling around the Earth. This shows that $F_c doesn't have to come from friction or tension. It can come from gravity itself. These appliances demonstrate how controlled, high-speed rotation can be used to separate substances, like separating dirty clothes from water. The rotational force gives the water sufficient centripetal acceleration to overcome gravity and fling the water out. Understanding $f_c equals mv squared slash r$ allows engineers to design these machines to be efficient and safe. Every time you spin a load of laundry, you are observing the physics of centripetal force at work. This is a straightforward calculation. We simply plug the given speed and radius into the acceleration formula. We are solving for $_c. Make sure your units are consistent, meters and seconds. Let's calculate. $_c equals 20(2)/$50. This tells us the magnitude of acceleration needed. The result is $8 This is the minimum acceleration needed to keep the car on the curve. This is the most complex type of problem. We are finding the critical threshold where the required centripetal force is only provided by gravity. We set $f_c equals mg$. Solving for $v$ gives us $v equals \sqrtg $r$. Plugging in the numbers, $v equals \sqrt 9.8 $10. This simple calculation yields the minimum speed. If the speed is less than this value, the coaster loses contact with the track and the motion is no longer circular. To wrap up our concepts, remember the big picture. Circular motion is fundamentally a battle against inertia. To keep something bending, you need a net centripetal force. This force is the total sum of all physical forces, tension, friction, gravity, pointing inward. Keep these core relationships, $_c equals v(2)/r$ and $f_c equals mv(2)/r$, front and center in your mind. They are the foundation for all of rotational dynamics that comes next. You've done the hardest part by mastering the concept. Let's review the relationships. We have 3 ways to describe the motion: acceleration, force, and period. Remember that $v$, $\omega$, and $t$ are all related. If you know 2, you can find the third. For instance, if you know the period $t$ and the radius $r$, you can first find the velocity $v$, and then proceed to find the force. Always check which variables you are given versus which variables you need to find. These formulas are your toolkit for the next few chapters. Once you are comfortable with the force and acceleration formulas, we move into energy. We will see how energy is conserved even when the force changes direction. Don't treat circular motion as a separate topic. It's a rigorous test of your understanding of Newton's laws in action. Whenever you see an object moving in a curve, stop and ask yourself, what is the net force pointing inward? This mindset, always looking for the radial, inward component, will help you solve any complex physics problem. You've mastered the hardest part, the conceptual leap from straight lines to curves. Great work. Imagine you are riding a roller coaster, and you pass over the very top of a hill. At this point, gravity is pulling you straight down, and the track is pushing you with a normal force. We need to find the normal force, at the peak. Remember that Newton's second law applies in the vertical direction. The net force must point towards the center of the circle. At the top, the forces acting are gravity, $mg$, pointing down, and the normal force, $and$, also pointing down, assuming the track is pushing you into it. Therefore, the net centripetal force, $f_c$, is simply the sum of these two forces. $f_c equals mg plus $. If we know the speed and radius, we can solve for $and$. This is a great example of how forces combine when things are moving in a circle, and it shows that the normal force isn't just about resisting gravity. It's about maintaining the necessary centripetal acceleration. Take a moment to visualize this force diagram. Where should the arrows point? This is one of the most elegant physics problems. A satellite orbiting Earth isn't being pulled toward Earth. Rather, the force of gravity is the centripetal force. Gravity provides the necessary force to keep the satellite moving in a curve. Let's set the gravitational force equal to the required centripetal force. $g\frac mm r squared equals \frac mv(2)r$. Notice how the mass of the satellite, $m$, cancels out. This is crucial. The orbital speed doesn't depend on the satellite's mass. Solving for $v$, we find that $v equals \sqrt \frac m$. This shows that the faster the orbit, the further away the satellite must be to maintain that speed. This principle governs everything from GPS satellites to deep space probes. Can anyone recall what $G$, $M$, and $R$ stand for in this equation? Let's analyze the relationship between the period $T$ and the radius $R$ for objects orbiting a central mass. Using our derived orbital speed formula, we can find that $T equals 2 pi sqrt frac r cubed and $. This relationship is often called Kepler's third law. If you double the radius, the period doesn't just double. It increases by a factor of $2 sqrt2, or about 2.8 times. This cubic relationship is powerful. It means that moving to a much larger orbit requires a dramatically longer period, even if the mass of the central object remains constant. This relationship is fundamental to astronomy and helps us model entire solar systems. Think about how a moon orbiting Jupiter would compare to a moon orbiting Mars. The difference in central mass, $M$, and initial radius, $R$, will dictate wildly different periods. What scientific field relies most heavily on understanding these orbital periods? When you see a car wash spinning you around, it feels counterintuitive. You expect to fly off. However, the brushes in the car are being held in place by friction. The friction force, $F_S$, acts as the crucial centripetal force, $F_C$. If the friction force were to drop below the minimum required $mv(2)R$, you would slip off. The speed of the car dictates how much force is needed to keep it moving in a circle. The engineers designing these washers must ensure the surface is rough enough and the speed is controlled to provide adequate static friction. This is a perfect, highly controlled example of required centripetal force in a non-ideal, everyday setting. If you were designing a safer, slower version, what physical parameter would you prioritize controlling? Consider a spinning top or a dancer who spins faster. To keep the spin going and maintain stability, the object must decrease its moment of inertia, I. This relates to the conservation of angular momentum. $L equals I\omega$. Angular momentum equals moment of inertia $, angular velocity. When the dancer pulls their arms and legs in, they decrease their moment of inertia, causing their angular velocity $\omega$, to increase dramatically, making them spin much faster. This principle is why ice skaters pull their arms in to spin faster. It's a beautiful demonstration of how rotational physics governs seemingly simple movements. The key takeaway is that while the total angular momentum is constant, the rate of spin changes when the mass distribution changes. Can you think of another example where pulling your limbs inward increases your rotational speed? Our understanding of circular motion is deeply tied to the revolutions of the planets. Before these figures, many people believed that celestial motions were perfectly circular, which is why the name circular motion stuck. However, Galileo used inclined planes to demonstrate that acceleration is constant, regardless of the direction. Later, Johannes Kepler, using meticulous observations of Mars, developed his 3 laws of planetary motion. Kepler showed that planets move in ellipses, not perfect circles, and that the speed changes throughout the orbit. This was a revolutionary shift. It forced physicists to abandon centuries of assumptions and develop the mathematical tools we use today, like calculating orbital velocity. This historical context reminds us that physics is not just equations. It's a story of challenging assumptions. Here is a classic problem. A ball enters a vertical loop at speed $v$. We need to find the minimum $v$ required for the ball to successfully complete the loop. First, we use conservation of energy. At the bottom, height $h equals $0. Energy is $k plus Pe equals \frac 12 mv(2). At the top, height $h equals $2r. Energy is $frac 12 mv_top 2 plus mg 2r. Setting them equal, $frac 12 mv(2) equals \frac 12 mv_top 2 plus 2 manager $. Next, for the ball to just make it over the top, the normal force must be 0, meaning gravity provides all the centripetal force. $mg equals m\frac v_top caret 2 r dollar, which gives $v underscore top, caret 2 equals gr dollar. Substituting this back into the energy equation and solving for $v dollar, we find that $v equals backslash is qr to 3 gr dollar. This minimum speed is critical. If $v dollar is lower, the ball will fall off the track. In this problem, the speed is changing with time. This means we have both tangential and centripetal acceleration. First, we find the tangential acceleration, $_t, which is simply the derivative of speed with respect to time. $_t equals backslash frac dividend equals 6t$m slash s caret $2. Next, we find the centripetal acceleration, $_c equals backslash frac v squared r dollar. Since $v t equals 3t caret $2, then $_c t equals backslash frac 3t squared caret 2 r equals backslash frac 9t to the power of 4 r dollar. The total acceleration, $a_net dollar, is the vector sum, $a_net equals backslash caret 2 plus $c caret $2. This illustrates that the total acceleration is not just the rate of change of speed. It must account for the change in direction as well. At $t equals $1 second, we can plug in the values to find the object's total acceleration. Understanding this vector combination is key to advanced physics. This problem combines two major topics: projectile motion, non-circular, and the general principles of energy. The projectile is launched horizontally, meaning its initial velocity is purely horizontal. We are interested in the speed when it hits a vertical wall at distance $d. We can use the conservation of energy. The initial potential energy is $mgh. By the time it hits the wall, it has lost potential energy and gained kinetic energy. Assuming no air resistance, the total mechanical energy is conserved. The initial kinetic energy is $frac 12 mv underscore initial caret $2. At the wall, the speed $v underscore impact is related to $v underscore initial and $h by $v underscore impact equals backslash is caret v underscore initial caret 2 plus 2gh. This shows that even when the motion isn't perfectly circular, the principle of energy conservation remains the most powerful tool for solving complex kinematics problems. The speed at impact is always greater than the initial speed because the height loss contributes to the kinetic energy. The most common mistake beginners make is thinking of centripetal force as a separate, magical force. It is not. Centripetal force, $F_c$, is merely the net force component pointing towards the center of the circle. If a book is tied to a string and you swing it, the tension in the string is the centripetal force. If you let it go, the force is zero, and the object moves in a straight line, Newton's first law. Another mistake is mixing up velocity. $v$ is the magnitude of the speed. $v_c$ is often used synonymously, but remember that if the object is accelerating along the circle, like a speeding car, its total velocity is changing, even if the radius is constant. Always draw a force diagram and identify the net force vector. If the net force is zero, the object is moving in a straight line. Circular motion beautifully connects to the work-energy theorem. Remember that work is defined as force times distance, and this work done changes the kinetic energy of an object. If a force, $F$, is acting on an object moving in a circle, the work done by that force is what changes the object's speed. For example, if gravity is pulling on a satellite, the work done by gravity is what changes the satellite's total energy. The rate of change of kinetic energy is equal to the net force times the velocity. This connection is vital because it allows us to find speeds and forces without needing to know the exact function of time for every component. Whenever you are asked to find a final speed given an initial speed, think first about the work-energy theorem. It often provides a much simpler path than integrating acceleration over time. If you master uniform circular motion, your next big topic is rotational kinematics. This is essentially the exact same physics, but applied to angles and rotation instead of straight lines. Instead of linear distance, $x$, we use angular displacement, $h$. Instead of linear speed, $v$, we use angular velocity, $\omega$. And instead of linear acceleration, $, we use angular acceleration, $\alpha$. The beautiful thing is that all the kinematic relationships, like the equation that relates $v_f$ to $v_$, translate directly. The key is remembering the conversion factors. $omega equals v/r$ and $alpha equals a/r$. Mastering this transition will prove that your understanding of basic linear mechanics was solid, and you are ready to tackle complex rotational dynamics. Let's pause and think conceptually. If an object is moving in a circle, its velocity vector is always tangent to the circle. If there were no net force, the object would move in a straight line, according to Newton's first law. Therefore, the very fact that the object is moving in a circle means there must be a net force constantly pulling it inward, the centripetal force. This force is what changes the direction of the velocity vector, causing the object to curve. It's crucial to remember that the force does no work on the object if the object's speed is constant, because the force is always perpendicular to the direction of motion. This conceptual understanding is more important than memorizing any single formula. We often talk about tension, especially when swinging an object. Does the tension equal the centripetal force required? Not necessarily. Tension is just one of the forces acting on the object. The centripetal force, $F_c$, is the vector sum of all forces pointing toward the center. For the swinging ball, the tension is the primary force, but if we added gravity, if the swing was vertical, the net force would be $F_net equals T mg$. The centripetal force must equal this net force. This distinction is key. $F_c$ is the result of the net force, not necessarily the name of the force itself. Always treat $F_c$ as the net force vector pointing inward. Let's take a moment to review the fundamental formulas. Notice that circular motion requires us to use both linear and rotational concepts. We have the basic acceleration components, tangential, $_t$, and centripetal, $_c$. The period formula is special because it is derived directly from the balance of gravitational and centripetal forces. And finally, the energy principle links everything together. All these concepts are interconnected. If you can solve a problem using conservation of energy, you likely do not need to use the full kinematics equations. This checklist serves as a map. These are the tools you need, but the real skill is knowing which tool to use for the job. Make sure you can derive these formulas, not just memorize them. Circular motion isn't just an abstract concept in a textbook. It is the foundation of modern physics and engineering. From predicting eclipses to designing safer amusement park rides, understanding $F_c$ is essential. It teaches us that acceleration is not just about speeding up, but also about changing direction. The fact that gravity dictates the orbits of planets, and that we can use the principles of that orbit to calculate everything from satellite launch costs to the speed of a projectile, shows the universal power of these concepts. This topic proves that physics is truly the language describing the mechanics of the entire cosmos.